We're in the waves topic, and we're about 3/4 of the way through it. And we're going to begin a discussion on a wave phenomena called the Doppler effect. You may have heard of this effect before. I'd like you to follow along with the student notes handout that I provided for you. Now, as I said, this is a phenomena that occurs in waves, and it requires motion. So you will not observe the Doppler effect unless there's motion of either the source of the waves or an observer of the waves. Probably one of the most common places to detect the Doppler effect is with sound. So I'm going to let you hear the Doppler effect. It's probably something you've heard before. Now you may have noticed that there's a change in pitch of that sound. It's a car that's approaching probably a microphone or some kind of observer. Starts out at a higher pitch, and after the car passes, the pitch lowers. Pitch is also known as frequency of that wave. So there's a change in the frequency. Listen one more time. If that car were not moving, let's say the car was beeping its horn and the horn produced that sound. If the car were not moving, there would be a single tone, single pitch, or a single frequency produced. But there was a variety of frequencies that you just heard. Namely, a certain tone that was a higher frequency and then a lower frequency tone. What we're looking at here in this picture is a set of spherical wavefronts. Now, if you remember from our discussion before, that's last year, wavefronts, which there's 3 of them here, are produced by a source of waves, and each wavefront that you see is in phase with the next wavefront thereafter. So these 3 sets of wavefronts might represent the crests of 3 waves. We're going to make use of this wavefront idea on the next slide. This is like a little water bug, and it's bobbing up and down, and it's producing the wavefronts that you see. Right now the water bug is stationary. If that little water bug, we'll call it a water spider, was to move toward point B, what would happen to the wavefronts? So that's the question I want you to think about. What would the wavefronts look like? Would they change shape? Would they stay spherical? How would their distribution look? Now, if you guessed they'd look something like this, well, you'd be correct. So what just took place? Well, that little water spider was moving toward point B. That means that as it released each successive wavefront, it was closer to the wavefront to the right towards point B. So those wavefronts bunched up. Whereas as it traveled toward point B, it was pulling away from the waves it was emitting behind it, which were heading toward point A. So those wavefronts are more stretched out. Now, if you think about what's going on, there's a full wave cycle between each front. So what happens to the wavelength as we go towards the B direction to the right? And what happens to the wavelength as we go towards the A direction toward the left? Hopefully you can see that one of the wavelengths has lengthened and one of the wavelengths has shortened. Take a look at it on the next picture. So here's a fire truck, and as the diagram shows, the fire truck's at rest. Now, it doesn't have to actually say the fire truck's at rest for you to tell that. If you look at the wavefronts, they're equally spaced for the observer behind the truck, which looks to be a man, and the observer in front of the truck, which appears to be a woman. Now the truck's going to move while it continues to sound its siren. Now, if you take a look, on the right side of the truck, or in front of the truck where the woman is standing, the wavefronts are bunched up. It's a smaller wavelength. Whereas behind the truck, where the man is standing to the left, the wavefronts are stretched out. That's a larger wavelength. This happens when the source of waves moves. This is the Doppler effect, or one of the effects of the Doppler effect. There's a change in wavelength. It's a real change in wavelength, that's actually measurable. It's not just a perceived change in wavelength. So a sound source or a source of waves has moved, and there's been a shift in wavelength. In one case, the wavelength is shortened in the direction of motion, and behind the direction of motion, the wavelength has lengthened. Now, if you remember anything about how frequency and wavelength can be affected, you might have an idea of what these observers are going to hear. They can't see the wavelength, but they can certainly hear the frequency. So how is the frequency going to be affected? What's the lady going to hear who's in front of the truck versus the guy who's standing behind the truck? Here's that fire truck going through town, and in place of the lady who was in front of the truck before, you have it looks like a vendor with a guy and a lady standing there. And what are they going to hear? The wavelengths are tighter together, and if you remember, frequency is how many. Literally the number of fronts that pass you in a second. Since they're more tightly packed, more wave fronts are going to pass them by in a second. Consequently, they're going to hear a higher frequency or a higher pitch. The people behind the truck, which is the fellow reading the newspaper and the other three people, those wave fronts are more stretched out. That means they're going to get less waves passing them in a second. That means the frequency they're going to hear is going to be a lower frequency. Consequently, a lower pitch. Pitch and frequency are tied together for sound, at least sounds that we can hear. Notice the question at the top of the slide. The second one says, how many different frequencies are heard at the hot dog stand if the truck travels at a constant velocity? And then there's a second question, at a changing velocity. Let's tackle the constant velocity one. How many different frequencies will they hear? So this is a situation where the truck's approaching at constant velocity, and the truck is just even, at least the siren is just even with the hot dog stand. And then the truck will pass them by, and they'll then be behind the truck. So there's three situations. Would that be three different frequencies? Remember, this is all occurring at constant velocity. So as the truck approaches, they hear a higher pitch. And that higher pitch stays a constant higher pitch. It's not continually getting higher and higher. It's one and only one higher frequency they hear until the truck meets up with the position of the hot dog stand. Now, when it's at the same position as the hot dog stand, they'll hear the actual frequency emitted by the siren. That's the same sound that the driver on the truck would hear because they're traveling with the fire truck. So now they're hearing a second pitch. And after the fire truck passes them, they're now going to hear a third pitch, a lower frequency, and a continuous lower frequency. So a continuous lower pitch the whole time. So they would hear three different frequencies. Again, let me point out, someone on the truck who's traveling with the source of sound does not get this bunching up or stretching out of wavefronts. So they don't hear the Doppler effect. Only someone who has relative motion between the truck and the observer will hear that Doppler effect, that change in frequency. So what would happen if this fire truck was moving along at 50 miles per hour, sounding its siren, and there was a car moving in front of it at 50 miles per hour as well, should be pulling over, but it's not pulling over? Would they hear a Doppler shifted frequency, or would they hear the actual frequency of the fire truck? Write that question down. See if you can answer it. Ask me again in class the next day. How about the second part of that question? How many frequencies are going to be heard at the hot dog stand if the truck is changing its velocity? What do you think? Would it be strictly three frequencies again? Would it be more? Would it be less? Write your answer to that down as well and ask me in class the next day. Now, in order to really get the most Doppler shift possible, you have to be directly in front of the truck or directly behind the truck. And you think of why. We know that there has to be relative motion between the source of the waves and the observer. So if they're exactly perpendicular to the source of the waves, is there any relative motion? Is the truck coming toward or away? What would someone who's exactly perpendicular, so not in front, not behind, but exactly perpendicular to the truck hear? Would they hear a Doppler shift? Would it be a higher or lower frequency? Would they hear just the regular frequency of the truck? Or would they hear nothing at all? Write that answer down and that question down. Remind me to discuss it in class. So here's kind of a summary of the Doppler effect as far as we've talked about it so far. You can see on the left diagram a police car who's sounding its siren is in motion. There's an observer in front of the car, one behind the car, and you can see the effect on wavelength and frequency. Hopefully this is an intuitive effect, one that you don't have to memorize, but one that makes sense. If it's not intuitive, you need to think about it, you need to explain it to yourself and write out a nice explanation so it's something you don't have to memorize, but something you can figure out. Now, here's a question. What happens, let's say, if the police car were sounding its siren, but it were parked, and the source of the sound, the police car, was not in motion, but the observer, the person who was hearing it, was in motion. So let's say they were traveling toward the police car in a car, going fairly fast, but the police car were parked, sounding its siren. What would happen? What would you hear? Frequency-wise, what would be going on? Wavelength-wise, what would be happening? Take a moment, write out your predictions. Pause the video, and when you're done with your predictions, start it up again. This is something we're going to have to discuss in class, so I'd like you to make a little note to have a discussion with me in class about it. That's going to be it for now. In addition to Doppler shifting sound, we can Doppler shift light. And tomorrow we'll talk a little bit about Doppler shifting light. Please read about it in your SoCoast book ahead of time. Talk to you later.